In our last lesson, we did resultant force. So today we are going to look at resultant velocity, which is our speed. So this says an airplane is traveling at a speed of 500 miles per hour at a bearing of 325 degrees. Once the airplane reaches a certain point, it encounters a wind velocity of 60 miles per hour in the direction of north 75 degrees west. We want to find the resultant speed and direction as a true bearing. Okay, so I'm going to draw myself a little picture that isn't 100% accurate, but it gives me something to kind of think about. So this is just my north, south, east, west here. So if my airplane's traveling 500 miles per hour, bearing of 325. So I know if I come around to here, so if my bearing starts here, this is 180, this is 270, 325. So if this is 360, I can back up about 35 degrees. It's about right here. So here's my 500 miles per hour. Right? And this is my 325 degrees. Okay, so then it encounters a wind velocity. This wind velocity is north 75 degrees west. So I'm going to go north and 75 degrees west, probably about right here. And it's only 60 compared to the 500, so it's going to be a lot shorter. It should also be a straight line or a straight segment. So again, not 100% to scale, but gives me the idea here. So this is 75 degrees right here. And then length of that, the magnitude of that vector is that 60 miles per hour. So my resultant vector would be like that. Although, I don't know why I can't draw a straight segment. Let me try that again. It's a little bit better. So basically, I'm trying to fly in this direction. The wind's pushing me this way just a little bit. So this is what I want right here. This is my picture, basically. That's going to help me figure out what my angles actually are. So I'm going to use for my vectors P for the plane and W for the wind. So the theta for the plane vector, so we had to use the bearing, but I actually want to know, like, this is the actual theta right here, right? So if, oh, just realized I didn't mark that whole thing. There you go. There's my 325. The orange one, though, the actual theta that I want, goes this way. So the purple one is almost at 360, right? But if I back up 35 degrees, so this part right here is 35, this part's 90, so my actual theta is the 90 plus 35, which is 125 degrees. Then theta for the wind, I started here and went 75 degrees, so this is 90 plus 75, so that will be 165 degrees. Okay. So using the trig, because I have my angle and I have my magnitude, then for the P, vector P, that's the plane, that's going to be the magnitude, which was that 500, times the cosine of theta, and for P that's 125, and then 500 times the sine of 125. Then the vector for the wind is going to be 60, because that's the magnitude for the wind, times the cosine of the angle that we found, which is 165, and then 60 times the sine of 165. Right, so there are my two vectors. So the resultant of that, when I add them together, P plus W. Well, when I actually add them, I'm adding them, so I'm going to use that and do that on my calculator. So that's going to give me, I'm going to make sure I'm in degrees, I'm going to get 500 times the cosine of 125. Oh, that put 5,000. Too many zeros. Okay. Times the cosine of 125. I'm going to close my parentheses. I'm going to add that to the x component of the second vector. So that's going to be 60 times the cosine of 165. Close my parentheses. So that is my x component. So now I'm going to do my y component. Go ahead and do them both at the same time. So 500, this time it is the sine of 125, close parentheses, plus 60 times the sine of 165. Okay, so now I have my x component and my y component for my resultant speed. So this is negative 344.744 and 425.105. Okay. So there is my resultant vector, but I want the resultant speed. That means I need the magnitude of that vector. So I'm going to need the magnitude of vector P plus vector W. So we know that that is, this is square root of a squared plus b squared, this being my a, this being the b. Now here's what we can't do. We cannot type those numbers back into the calculator. Now, if you are using an 84 or a calculator like that where you have some store functions, you could go about this a little bit of a different way, but I think that the majority of you are using a Delta Math or Desmos type calculator, so I'm going to show you what we can do with these when we can't really store our values, but we have to use our exact values. Okay, so there's a little bit of calculator stuff. Here is, this is A, this is B. So when I want to take the answer, if I hit the answer button right here, that's going to give me this last answer, this 425. So basically I need to square both of those answers that I have, add them together and take the square root. So I'm going to have the square root of the last answer, that 425, it lets me know which one it is, and I'm going to square it, plus I also need to take this answer right here and square it. But I can't really grab this answer. And even if I use this whole number, that's still not, I mean, there's more stored in there than what I can see. So even though what tells me this is what we're using, it's actually using more decimal places than that. So I need to actually take this and square it, but I don't have to retype all that. So I'm going to open my parentheses. I'm going to highlight this. Then with my keyboard, I'm going to do Control C. Then I'm going to come back down here. It went ahead and closed my parentheses for me, and I will do Control V. And it puts that whole thing in there, which means this is going to give me, this is this number right here. But I'm not done yet because there's my parentheses around all of that. Then on the outside of this, I need to square this. So there's my a squared plus b squared. I get 547.323. So that is my resultant speed. So that means that I have 547.323, and this was in miles per hour. So miles per hour. Right, so I still need my angle. So my theta is the tangent inverse of b over a. So I'm kind of in the same boat that I was before. But now, when I go back over here, if I use the answer above, that's not an answer I want. But I have both of these things already typed in. So this is, and I got to keep track of them. This is my A, this is my B, because I have to put it in there in the correct order. So function, tangent inverse, and I want this to be a fraction. So in the numerator, B goes in the numerator. So I'm going to copy this, Control C. That's the B, it goes in the numerator. Control V. A is the denominator. So I'm going to copy A, Control C, put it right there, Control V. There's the tangent inverse. I get negative 50.959. All right, so that is negative 50.959 degrees. But I got to make sure I answer this correctly. It says a true bearing. Okay, true bearing means that it starts up here. All right, true bearing would mean I start here and rotate around. Okay, but the answer that the calculator gives me is a theta answer, like our unit circle that we're used to. So this negative 50 would actually put me down here in the fourth quadrant, right? So that's the negative 50 something. But as always, that's not necessarily the answer that I want. I'm still thinking in terms of theta. If this is my vector, negative, positive, that means I'm pointing towards the second quadrant. So to get my second quadrant angle here, so this is the 50, blah, 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 then I would need to take this and I'm going to add 180 so I can get that number. Okay, so I'm going to go back to my calculator, use my answer plus 180. I get 129.040. But all I really care about is the fact that it's like 129 point something, right? And then, so that puts me there. The bearing that I want starts here, goes around like this. That's a true bearing. So I got to figure out how to use these numbers. Turns out, I really didn't even need that 129. I didn't need to know necessarily what this angle is. The 129 actually starts here. I didn't actually need to know what that is because, if you recall some stuff from geometry that's important, you have vertical angles right here which are congruent. So if this is 50 something, this is 50 something, right? And what I need to do is I need to figure out how much this is. So if this is 90, 180, so this is 270 plus this 50 number. So I would like to get my 50 number back. So since I added 180 to get that, I'm going to take my answer and subtract 180. I got my 50 number back without typing in any decimals, but I want that to be positive because I want to add 270 to it. So I'm going to multiply by, oops. Let me do my answer. I'm going to multiply by a negative 1. So now, then I put a plus, my goodness. Okay, so now I have that 50 number, and it's positive. And remember, from right here, since this is 50, I could take 180 minus that 129. It would give me that number back, but that's why the vertical angle should make sense. This is 270 plus that 50. So now that I have that 50, so I'll use my answer plus 270. There's my number, 320.959. So my theta that I want for my answer, which is the bearing, which is beta, is 320.959 degrees. Make sure you're actually thinking about your answers and not just getting numbers off of the calculator. You have to reason through and understand what this all means. All right, so let's look at number 11. It says a baseball player runs forward at 15 feet per second and throws a baseball at a velocity of 80 feet per second at an angle of 20 degrees with the horizontal. what is the resultant speed and direction of the throw? Okay, so we're not asked for a bearing here. We're asked for a direction of the throw, and that's talking theta. So we want to think about what's happening here. So he's going to run forward, right? So running forward at 15 feet per second. Forward would just be your angle 0, right? So here we go. This is at 15 feet per second. And then he's going to throw at 80 feet per second with an angle of 20 degrees. So we'll have a 20-degree angle. This vector is much longer because this is 80 feet per second. Totally not to scale, but that says 80 feet per second. And my angle right here is 20 degrees. So my resultant vector is actually right here. Okay, so our angles that we need are theta. We'll do the player and the ball. So the theta for the player's running forward, so his angle is 0 degrees. The theta for the ball, that's 20 degrees. So it was kind of given to us. We didn't have to figure it out from bearing, but that's what's happening there. So then our vectors, our player vector is, see, 15 feet per second times the cosine of the angle, which is 0, and then 15 times the sine of 0. Then the ball, that's going to be 15 times the cosine of 20. No, it is not 15. Gosh, I did that again. Sorry about that. I need the magnitude for the ball, the velocity of the ball here, 80 feet per second. So this is 80 times the cosine of the angle, which is 20, and then 80 times the sine of 20 degrees. All right, so we're going to save ourselves a little bit of typing in here because we can figure this out. These are values we should know. The cosine of 0 is 1, so 1 times 15 is 15. The sine of 0 is 0. 0 times 15 is 0, so that makes that a little bit easier there. So that when I add them, player plus ball, to get my resultant vector, instead of typing all this in, I can use the 15 and the 0. So I'm going to go to my calculator. I'm going to clear off all this mess. And then I'll have the x component will be 15. That's the first one, plus the second one, which is 80 times the cosine of 20. And then I'm going to have, for the y component, it's 0 plus 80 times the sine of 20. So no need to type in. Why did I do 80? Oh my goodness, y'all. It's 0 plus this, plus 80 times, I don't know what I said. I think I said it right and did it wrong. I probably said it and did it wrong. I'm not putting the 0 because it's 0, but I have to add that to 80 times the sine of 20, which is what I should have typed in. I promise I know what I'm doing. And there we go. So there are our two components for our resultant vector. So this is 90.175 and 27 point, can't even do a decimal, 27.362. Okay. So now I need to find the magnitude. Magnitude of vector P plus vector B. That's this one right here. Remember, I can't type in those numbers. So when I go back over here, that's going to be the square root of my last answer squared, because that gives me this one, plus, I'm going to open my parentheses. I need to take this answer and square it. So take that, Control C, put that in there, Control V. Don't forget to square it. Make sure you have the two things that you want, and you get 94.235. So that means he is throwing the ball at a velocity of 94.235 feet per second. Okay. So that is the resultant speed, the magnitude of that resultant vector. Then I'm going to need theta. That's equal to the tangent inverse of, remember that's b over a. So go back to my calculator. Tangent inverse. B, make sure you know which one is which. This is B. So I want a fraction. I'm going to put the B, highlight that, Control C, put it in my numerator, Control V, highlight A, Control C, put it in the denominator, Control V. So there's the tangent inverse of that. And I get 16.879. That is theta. And because it wasn't asking for any kind of bearing, it's just the direction, that is my answer. That is my theta. Okay. All right, let's look at the next one. All right, so our boat heads directly across a river with a velocity of 28 miles per hour. The river is flowing at 12 miles per hour. We want to find the magnitude and direction with respect to the shore of the boat's resultant velocity. Okie dokie. So let's say that this is our river. This is the shore. This is the shore. So our water's in here. All right, so our boat heads directly across the river with a velocity of 28 miles per hour. So it's going across the river. This is 28 miles per hour. The river is flowing at 12 miles per hour. 12 miles per hour. So our resultant vector looks like this. So what this means is if you're trying to go directly across the river to the other shore, you're not going to be able to do that if the river's flowing at all. So since the river's flowing this way, even though you're heading directly for that spot, this is where you're going to actually end up. Okay, so we need our angles for our different vectors, so we'll use the boat and the river. So the theta for the boat vector. Okay, so here's the boat. This is 0, that's 90. And then the theta for the river is 0. Now on the last one we did, even though we had a degree of 0, we actually wrote in our trig stuff, but I don't have to actually do these with trig. The reason I have to do that is when I have an angle, like I don't know exactly what the components would be for these vectors, but these I clearly do. Because for the boat vector, if I'm starting here, I'm not going left or right any. I'm just going straight across that 28. So this vector has to be 0, 28. If you want to set it up with trig, knock yourself out, but you're going to get the exact same thing. Then the river, if I'm starting here, I go to the right, 12, but I don't go up or down any. So this is 12, 0. Which means the boat vector plus the river vector equals 12, 28. So then the magnitude of the boat plus the river vector is going to equal the square root of 12 squared plus 28 squared. We can go ahead and do that on the calculator. So I'm going to clear all this mess off. My square root, and that will be 12 squared plus 28 squared. And that gives me 30.463. So this will give me 30.463. and that is miles per hour. Still need the angle, so theta is the tangent inverse of b over a, so that's 28 over 12. I don't have to do anything fancy because these aren't decimals that I found. And when I do that, tangent inverse of 28 divided by 12, I end up with 66.801. 66.801 degrees. But as always, I got to double check and make sure this is really what I want. So this is not bearing. I want the direction, but it specifically says with respect to the shore. Well, this is the shore. This is my vector. So this is my angle, which if I think about this as starting at 0, then it's just that theta. That is my angle. I don't have to do anything fancy to it. That's theta, and I'm done. So now we have a drone. A drone is flying at a speed of 40 miles per hour in the direction of south 70 degrees west. There is a wind of 15 miles per hour in the direction of south 10 degrees east. Find the resultant magnitude and direction as a quadrant bearing of the drone. Okay, so drone is flying at a speed of 40 miles per hour, direction of south 70 degrees west. Okay, so I need to think about, here's my little, just my north, south, east, west, so I can get my bearing down correctly. If I'm going to go south 70 degrees west, it would be like this, and this is 80 miles per hour. Then I have to add to that the wind of 15 miles per hour going south 10 degrees east. So south 10 degrees east, it's me like right here, and that is 15 miles per hour. So my resultant vector would look like this. And then I have to figure out my angles in terms of theta so I can use them mathematically. So I know that this angle right here, the way I got this one, it was south 70 degrees west. So I came down south and then swung 70 degrees west, which means this right here is 20, right? Because if this is 70, that's 20 to get that 90. So this is 20, this is 180. So if I do that 180 plus 20, that's going to give me 200 degrees. So the theta for the drone is 200 degrees. Then the theta for the wind, I went south 10 degrees east. Well, I know if I start here and go to here, that's 270, add another 10, and I'm going to get 280 degrees. So those are the pieces that I need. It would probably be to your benefit to pause this, try and work this out, and then come back and see if we agree. So my drone vector, I'm going to take that 40 times the cosine of the drone angle, which is 200, and then 40 times the sine of 200. The wind vector is going to be a magnitude of 15 times the cosine of the wind angle, which is 280, and then 15 times the sine of 280. Then I'm going to add them together. Drone vector plus wind vector. Going to need my calculator for this. So I'm going to clear all this mess off. I'm going to get my x component first, so that's going to be 40 times the cosine of 200. I'm sorry, I said plus again. 40 times, I don't know what I said. 40 times the cosine of 200. I did it right, I'm just not sure what came out of my mouth. And then I'm going to add to that 15 times the cosine of 280. That's my x component. Now I'll get my y component, which is 40 times the sine of 200 plus 15 times the sine of 280. And that's what I get for those two. Okay, so there's my resultant vector. Let's go write that down. This gives me negative 34.983 and negative 28.453. All right, so I need my magnitude, which means I'm going to have to do some fancy calculator stuff again because that's the square root of a squared plus b squared. So I'm going to use these numbers but not as decimals because I don't want to be off on my rounding. So I'm going to come back over here and I want the square root of my last answer squared plus, open my parentheses, this answer. So I'm going to do that. Control C, place it in there. Control V. Not done because I have to make sure that I square that. And that gives me 45.093. So that is 45.093. And this is the resultant magnitude, which is a speed, so velocity, miles per hour. There's that part. Then I need my theta. Theta is the tangent inverse of that b over a. Right? This over this, but again, got to make sure that I do this correctly. So I'm going to have the tangent inverse of, let's be a fraction. This is b, so I'm going to highlight that, Control C, put it in the numerator, Control V, highlight A, Control C, put it in the denominator, Control V. So I get 39.123. So that's 39.123 degrees. But again, we have to think about what it is we're actually wanting, because that's not my answer. What this gives me, that's a 39-degree angle. It's up here in the first quadrant somewhere, right? This is negative, negative. So I actually want the third quadrant version of that. So since I want the third quadrant version of that, I would just add 180 to it. But since I don't want theta anyway, I'm not going to bother even adding 180 to it. Think about what you have. If this is 39 degrees, this is 39 degrees because they are vertical angles. What I want is a quadrant bearing, meaning how do I get over here? I would clearly not go north. I'd have to go south and then swing west. So my answer is going to be south something west. And I got to figure out what that angle is, right? It's whatever this angle is. Well, if this is the 39-degree angle, so is this because they're vertical angles. I want this part of it. So if I just take 90 and subtract this part, I'll have the angle I want. So I'm going to say 90 minus that last answer, and I get 50.877. So it's south, then 50.877 degrees west. I'm going to rewrite that. I should have spread out my S and my W a little bit better. Oh, come on. All right, so I'm going south 50.877 degrees west. That is my quadrant bearing. All right, so let's talk about horizontal and vertical components. This says a vector can be resolved into horizontal component and a vertical component. Right? That's basically by x component and my y component. The horizontal and vertical components are also called rectangular components. Because the rectangular components form a right triangle, you can use trigonometric ratios to find their magnitudes. Okay, so this is a lot like what we've been doing, but we're just talking about the pieces a little bit different. So let's see how this works. It says Danica is pulling a sled with a force of 400 newtons using a string. If the string makes a 35-degree angle with the ground, find the magnitudes of the horizontal and vertical components. All right, so she's pulling a sled with a force of 400 newtons using a string. And the string makes a 35-degree angle with the ground. So here's the ground. Here's the string. This is 35 degrees. This is 400 newtons. Right? And what I want to know is the horizontal and vertical components of this vector. So it says we can use, up here, you can use the trigonometric ratios. We know that this is our horizontal component, or our x component. This is our vertical component, or our y component. So, if I want to know what x is the adjacent angle, this is the hypotenuse, so I would use cosine. So the cosine of 35 degrees is equal to x over that 400 newtons. Because this is a triangle, we're talking lengths here, that x is always going to give you, or whatever you find is always going to give you a positive number. So this is going to give you the absolute value of x because it could be a negative component. But when I multiply, then I'm going to get 400 times the cosine of 35 equals the absolute value of x. This is your mg cosine theta, right? Just like you've been doing in physics if you're in physics. So then I get that the absolute value of x, I go to my calculator and type that in, 400 times the cosine of 35, you get 327.661. 327.661. Then, because she's pulling it this way, she's got this is a positive and a positive. So that means your horizontal component is 327.661 newtons. So then to find your y component, that's opposite in hypotenuse, so that's sine. So this will be sine of 35 equals the absolute value of y over 400. So 400 times the sine of 35 equals the absolute value of y. That's your mg sine theta. So on my calculator, I'm going to do 400 times the sine of 35. And that's 229.431. So the absolute value of y is 229.431. But nobody asked me for y or even the absolute value of y. It asked me for the horizontal and vertical components. And so vertical, this is, you clearly see from what's going on, it's positive. So your vertical component is 229.431 newtons. Okay, there you go.